So my name is Andrew Lord. I work for BT, Senior Manager of the Optical and Quantum Group in research in BT, and really happy to speak at this event. And this particular section, section 2, is focused on quantum cryptography and what is the threat to security for quantum, and what do we do about it. So I'm actually not going to talk about quantum for a few minutes. Okay, so put your quantum hats to one side and let's think about a completely different space. So Tom, you're sitting there and I'm going to send you, well, I'm going to pretend to send you some secure data, okay? How do I get this data to you securely, Tom? I need to encrypt it, okay? So I need to lock the data up so that someone in the middle can't, even if they can read it, they can't make any sense of it. Locking up data involves a key. I want to send data to you, I need to lock it up using a key. Now that whole process happens all the time, every day, and the common protocol for locking up data is known as AES 256. This is a protocol, it's a metric protocol, and it's a key that enables me to lock up data and you, Tom, to unlock the data with the same key. Okay. Now you're probably screaming at me, well, how do I get that key, Andrew? You haven't solved the problem, you just moved it. I can see how you're now getting encrypted data to me, but how do you get the key to me? And key distribution is a really significant and big topic that we need to address. Let's just think, out of the box, how do I get some keys to Tom? I might put a whole load of keys in a suitcase, padlock it to somebody and fly them to Tom in California. And if you're smiling, that happens all the time, right? That is a very common way of doing key distribution. For situations where you need absolute guarantee. There are other ways of distributing keys using secrets and things, but actually the main method is much more prosaic than that. It uses the network itself to distribute keys. And we distribute keys using other keys. Okay. So we use a key to distribute a key. Now, I know this is confusing, so I want to spend a few minutes just clarifying it, because this is really important for the next section of this talk. Keys, to distribute keys, this whole area is known as public key cryptography, PKC. If you Google that, you'll find millions of hits. PKC is a method for me to get a key to Tom. And it uses another key, but actually it doesn't just use one key, it uses a pair. And this pair of keys is a private and a public key that go together. The private key is owned by Tom. He doesn't let anyone see it, but his public key is public. So I get hold of it. I get his public key, which anyone can have, and I use it to encrypt a secret key. I then send it to Tom, and Tom uses his private key to unlock that secret key. Then we both have a secret key, the same secret key that we can use to transmit data. I'm just going to say that again because I think it helps to go through this twice. It's complex. We're going to distribute a key. We're going to do it by setting up public key cryptography between us. Tom has a private key and a public key. I use his public key to encrypt this secret key. Send it to Tom, and he uses the private key to decrypt it. You can't decrypt it any other way. Public keys don't decrypt. They only encrypt. They only go one way, and that's crucial. But the public and private key are completely linked. They're a pair. It's just that if you have the public key, it's very hard to work out what the private key is. Probably billions of years of computer time. Well, at least it was until quantum computers came along. That problem of finding private keys from public keys suddenly got a lot easier. And they got easier because quantum computers take advantage of something called Shor's algorithm to cut through that whole problem. Now, what is Shor's algorithm? And don't worry, because this is a 2-hour talk, which I'm not going to do right now. It's highly complex. But you can see there, actually top right, you can see what we're seeing here is a quantum computer, and it's processing a public key to make a private key. Okay, and this, in principle, will break keys when the quantum computers are strong enough, but they're not strong enough yet. But it is motivating the whole of the security industry to get that act together, to the point where now, 9 or so years ago, NIST launched a competition to find new codes that were not susceptible. Now, these new codes are called Post-Quantum Cryptography, PQC. In other words, codes that we don't believe could be broken by Shor's algorithm or anything else. And note my careful phrasing there, we don't believe will be, because you try proving that, very difficult. So we're in a world now where we're worried about quantum computers. We're concerned that at some point they will undermine security. People could even hack into your data now, not decrypt it yet, but just wait. And when a quantum computer comes along, they'll break it. So there's a concern now that we're sending data that is potentially in future decryptable. And the two solutions, one is to find a new algorithm, PQC, and that's a very big topic. I'm not talking about that, but you can see at the bottom there a timeline of plans for introducing PQC, very important. We all hope that carries on. Or using quantum to fight quantum, something called QKD, and I want to spend the rest of this second section looking at sending keys in a completely different way, not using algorithms at all. So I'm flicking to the next slide. This slide's called "What is quantum key distribution?" Sounds like I'm getting a bit of latency in it updating. Hopefully you're getting that slide, Tom.
When you advance and then move back, it seems to fix it on our end.
Tom, I'm going to now send you some keys in a different way. I'm going to send them on single photons of light, these little red circles, one at a time, and I'm going to send them from me to you. And each of these photons is in two states. It's an up and a down state. It hasn't decided what it is yet because you haven't looked at it. It's fuzzy, just like those atoms on the very first slide. Send them to you one at a time, and as you detect them, you will measure them, and you will generate some keys. Okay, and we have a conversation between us to decide which of those photons are used to make keys. And this is a completely different way of distributing secrecy. And all I really want to point out here is that there's two reasons why this is, at least in principle, hack-free or can't be decrypted, can't be broken. The first reason is this: these red circles are single photons. Okay, so if someone was to hack or tap into this fiber and steal a photon, it won't get through. So Tom, if someone steals one of those photons, you don't get it. And so therefore, it can't become part of your key because you haven't received it. So stealing doesn't work. And by the way, you can't steal half a photon. You either steal all of it or none of it. That's the thing about photons. So it's indivisible. So what if the hacker was a really, really clever and had a massive quantum physics department in a university and decided, instead of stealing, he was just going to measure it and then let it carry on its way? Or maybe extract it, reproduce it, and put it back so that no one would know. Now, quantum physics doesn't let you do that. Quantum physics forbids you from cloning. There's a no cloning theorem in quantum physics that says for quantum particles, you can't copy them. If you copy them, you change them, and the change is immediately detectable. Now, this is crucial and fundamental to a lot of what I'm talking about. I'm relying on quantum physics to make my security here completely unhackable by definition. So it's provable. It's not something that I hope or that I don't have a strong enough computer yet. This is in principle always going to be unbreakable. Because just trying to interfere with this process will change it in a detectable way. An alarm will go off and it's broken. Now, just to put a caveat on that, we need to make sure that when we build these things, they're secure. So just taking the idea is one thing, but to actually implement it properly is important as well. What have we been doing about this? So I'm very keen to commercialize this. We've been working at this for many years there. And the timeline in BT is culminated in a trial started in 2022, based in London. So we have a commercial oriented quantum trial in London. we worked on QKD quantum many years ago, but it was way ahead of its time. More recently, we've been building research connections, and in the last 3-4 years, we have now a commercial trial in London, and I'm going to spend the next 3 slides talking about that and talking about some of the customers that are on that trial. And then I'm going to be honest about how it's working and how it's not working, because it could go better. And I'm going to pose some questions about this whole industry and where we are. And I'm going to be honest. So this is our trial, launched 3 years ago. It's in conjunction with Toshiba, who I would describe as best-in-class QKD. So we have their equipment, and it's installed in regular BT Exchange buildings in London. If I took you to see it, it would look just like any other telecoms equipment. Okay, it's built into our regular alarming and monitoring service, so if it breaks, our network operations center hears about it. So it's in all respects ready to go. This could be used to build a QKD commercial proposition. Nothing stopping it. Currently, the phase we're in is trials with some major customers. I'm going to talk about those in a minute, as well as a bit of a deep dive in terms of the technology, because the technology is really fascinating. This is the kind of detailed topology of the trial. You can see there's 3 nodes, 2 red ones in London and 1 in Slough. Slough is near London, and it represents the data center district, data center community. And we're very keen on data centers for QKD, as will be apparent in a minute. So what about customers? So we have a major bank, HSBC. We have a professional services company, EY, Ernst & Young. We're partnering with Toshiba, AWS, and Equinix. Equinix, if you haven't heard of them, run data centers in cloud. So it's quite a team. And the thesis is that we really want to explore customers wanting to do secure backup to the cloud, to do secure financial transactions, to make sure their customer data is secure, etc. So a whole range of kind of use cases associated with this trial. And someone earlier asked about companies. I think this set of companies is good and gives us some leverage to explore the art of the possible. But I would like more customers. And there is definitely capacity for more on this. Okay, the trial itself is very commercially ready. So it's you can plug and play. It has access to customers' communications rooms. So we have fibre going right the way into HSBC's central office in Canary Wharf in London. Carries quantum all the way through the network. It's completely managed using software-defined networking. We plan to extend this to satellite QKD in a couple of years so that we have global QKD connectivity. And at the moment, that the objective of the trial is not, does the physics work? We know that. It's what are the use cases? What's the appetite? What could be charged for it? And how do we see this progressing into something that's part of BT business as usual?
Andrew, a question for you on one of those items. So a couple slides ago, and you don't need to go back to it, especially with our slide issues, you seem to imply that quantum key distribution was highly dependent on optical photonic transmission. But you did just note here that you were looking at satellite quantum key distribution, so it's not tied to photons in fiber. You can do this key distribution over other media.
It's tied to photons.
Yeah, okay, and photons I can see, sometimes I can't. Yeah.
The photons don't need to be in fiber.
Got it.
But they need to be photons. And and the photons need to have enough energy so that it can't be radio. So I can't do QKD to my mobile phone because there's no actual light photons. It's radio. They're still photons. They're radio waves, but the radio waves are too low in energy per photon. So there's a lot of physics here. Short story is it needs to be light photons of some form. Now that they can be in fiber, they can be through space. They could be between satellites, but they have to be optical photons.
And it is not a quantum distribution method because the photons are observable and are unchanged upon being observed.
That's what stops it being hacked, yeah.
Right.
So inbuilt in this system is an alarm. And if someone did that, if someone were to intercept in the middle of this system, an alarm will go off saying this photon has physically changed. It was in this state and now it's in this state. How is that? Someone has changed it. So if someone were to measure a photon that we weren't expecting, someone that shouldn't be, we can detect that. So we're detecting premature quantum physics, if you like. This picture here then is a detail of the design, and I'm not going to go through it, but I did want to go a bit deeper to show that it's not just boxes connected. There's a lot of thought and engineering and architecture that's gone into turning QKD into a full solution. That's really important. So regular networking skills, companies that know how to make networks are important. It's not just physics. The QKD sits at the bottom, but there's loads of other stuff. There's a key management service, KMSs. There's data coming in that's being encrypted. There's WDM. This is combining wavelengths. So there's lots of different colors of light all being combined onto the same fiber. And this is just the first level of detail. There's many levels underneath this. So I do want to get across the impression that this is, the physics works, but there's still some work to do in terms of engineering. This is a very quick slide just to showcase Equinix, the data center company, who we are now building QKD connectivity between two of their data centers, one in Slough, one in central London, for the purpose of them offering it to their customers. If they have a customer that has data that is so sensitive that it should be quantum secured, they will be able to, in the next month or two, when we finally complete the connection, be able to use our QKD link. So we're very excited about this extension of the trial with Equinix. Okay, so I'm going to go to some of my learnings. This is where I'm going to be honest, and there's no point in me glossing over some of the problems. So I'm going to be honest about them. The good news is it works, and we've been really pleased with the trial. I don't have any real issues with the performance of the trial at all. It doesn't break, it works well, it does what it says. We would love more customers. So why haven't we got them? This is interesting because I present quantum to customers with talks like this every week, literally. Customers come to BT all the time saying, tell us about quantum. So I do this so often, and yet it doesn't translate yet into real customer traction. There's still a reluctance. There's some good use cases. I would like more. I'd like there to be more than just financial interest, because I think there is a lot of scope. Overall management is fine, needs doing, but we've done it. What is the commercial viability when you add satellite? I think it becomes a global quantum secure network. That sounds compelling to me. And I think probably the one thing that we still do need is that the major telecom vendors, the Nokia, Cisco, Ciena's, Huawei's of the world, start to integrate quantum into their own products, which would make it much easier for telecom operators to consume. So for sure, we still need some maturing in that part of the market. But there's a problem. Here it is. This problem is that people like NIST, the National Cybersecurity Centre in the UK, the NSA, and many countries in the West still not convinced about QKD. They have issues with it. The issues are around things like its hardware, so it's expensive. It doesn't get you all the way to your phone or your computer because it's fiber, as we talked about. So it doesn't do the whole thing. So what's the point? I have a much better solution with PQC, which I talked about. So why would I need this anyway? And finally, are you sure you're implementing it properly? I mean, we know the theory, but what about the box itself? How do you make sure that the actual box that you bought from a vendor you've never heard of, possibly, is secure? So we have a lot of industry questions that we're trying to answer, because these problems are good ones, right? I'm not criticizing this at all. I'm saying this is a very hard-nosed reality of building a security product. This is what you're going to get. And for sure, to this point, very physics-based quantum industry is having to learn to deal with some hard-nosed security questions. And this is a big part of the reason why it's not progressing more quickly.
Andrew, a quick question on this. So we've seen in many times in other key technology breakthroughs, there needs to be a compelling event. And I think there's enough of quantum computing is not stable, practical, and useful in production enough yet that I don't have a sufficient motivation to really focus on solving the issues at scale that you've talked about. What's it going to take? What's going to be that compelling event that really drives some of these issues to conclusion?
Well, obviously, when someone makes a quantum computer that breaks RSA, and suddenly all of our networks are undermined.
Yeah.
But that's too late. Way too late. Rolling out a new security protocol is years. For a big complex network, it's 5 years or more. You probably have thousands of end devices that need upgrading. You can't do that instantly. So it's a really good question, because we are continually having the discussion. You need to think now. Don't wait. You can't wait until that event happens, because it's too late then.
Wholly agree with that. And the lag it takes to get new encryption schemes through NIST, just in the US, right? And then deployment into hundreds of thousands, millions of devices that need to be protected. That's going to take years, and that needs to be well ahead of when RSA is actually broken.
Yeah. Now, we know that, and the people that care know about that, but it's trying to just get that mindset further down into the industry. That's a battle of minds at the moment. So yeah, I fully agree. I just want to flag this slide, which shows a project that we're working on to try to put our house in order. So this is all about making sure that our own assurance and standardization, the conformance of QKD is done. Because at the moment, we might have a box that in principle is great physics, but if you go and buy it, how do you know that it's doing what we said it's doing? You've got no way of knowing. And opening the lid isn't going to help, because it's tough physics in there. So that's no help, is it, for me to say, trust us, we've got some really cool physics. That doesn't help me sell anything at all to an industry that is very security-minded, very risk-averse. So this is the project where we're really trying to do that work of defining tests to make sure that our own assurance of our own industry, of our own technology is in place. We just want to put that out. So this concludes section 2. This was the big section. The last two are quicker. This one, what have I said? Quantum computers are going to undermine cryptography. New algorithms exist. They are starting to be rolled out. That's going to take years, but they exist. Quantum key distribution is another way of doing it. I think you could probably use both. And if you're very risk averse, why not combine them? It has some detractors, though. It has its critics, and they're very well-known critics. And that's one of the reasons why it's not making as much progress as it might. However, I think that will change, and I'm expecting to see, as a volume ramps up, we will see cost of that technology reducing. However, I'm still worried that in the end, QKD will end up at best being very niche. And I don't want it to be niche for this reason, because a lot of the technologies in QKD are going to help me do what I want to do next, and that's section 3, and that's build a quantum network.